Section 4.3 Graphing Techniques. Now in this section we will see graphing functions using vertical and horizontal shifts, and graphing functions using reflection, and graphing a function by using multiple transformations. Now the first one is graphing functions using vertical and horizontal shifts. Now assume you know the graph of function y equal to f of x. So this is the graph you already know, and you are asked to graph y is equal to f of x minus c and f of x plus c. So in this case, if this is the naive function, if you want to get the graph of this function, you need to shift the graph of y equal to f of x c units up. So it's a vertical shift. We do it this way. It's a vertical shift. Or we do it downward, because if we have f of x, if we are given y is equal to f of x minus c, then we can shift the graph of y equal to f of x c units down, and it will give you the graph of y is equal to f of x. This is how we state it here. The graph of y is equal to f of x plus c is same as the graph of y equal to f of x shifted upward c units, and the graph of y equal to f of x minus c is the same as the graph of y equal to f of x shifted downward c units. Let's look at this example. Sketch the graph of y equal to x squared plus 2 and y is equal to x squared minus 2. And of course here, first we will start with y equal to x squared. Before doing this vertical shifts, I want to remind you that you can make the graphs all the time by using the table and take the points and make the graph. You can make the graph, but here we want to use the vertical shifts because we know y is equal to x squared. This y is equal to x squared, we already know it. And then it's x plus 2 is wanted, so it means we will shift it 2 units up, so it will go 2 units up. So let's say this is 2, 0 will come to 2, and that will be y equal to x squared plus 2. And then minus 2, it will go 2 units down, so it will go, okay, this will go down now 2 units, so it will go to minus 2, and we will have this. And to verify your graphs, you can take some points and see if they are compatible with the graph. So you can take like 0. When you put 0, you got y minus 2. 0 minus 2 is on the graph. Yes, it's here. It's okay. And you can check the intercepts as well. So these the vertical shifts are, if applicable, if you can apply them, and if it is possible to apply, let's say, then it's a shortcut of making the graphs, sketching the graphs. But of course, you have to know the basic function, the graph of the basic function here. Our basic function is x squared. We already know how its graph look like. Now here is obviously what I did. Let's look at this try and check exercise. Sketch the graph of f of x equal to the absolute value of x minus 2 and f of x equal to x cubed plus 5. Now, there are several ways of graphing it, but the one way is the simplest way is making the table and finding the points and putting in the graph on the Cartesian coordinate system and make the graph. But of course, we will not do it here. We want to use the shortcuts here, the short way. We will check if it is possible to make some vertical shift and get the graph of this one. Now the first thing you have to see is this one here. This is a basic function. We already know this is the absolute value function, and we know its graph. What is its graph? So its shape is like a V. So it's a V shape. So this is y is equal to the absolute value of x. Now, if you want to make the graph of y is equal to absolute value of x minus 2, as you see, what's the difference here? The absolute value of x, but here it's minus 2. So it means it will go 2 units down. 2 units shifted 2 units down, and then you will get y is equal to absolute value of x minus 2. And if you want to make sure the points are okay, you can put some values here for x and y, like this is y is absolute value of x minus 2. You can pick some points and verify your graph. Let's put 0 and y equal to minus 2. So it means it's here minus 2. And let's put some more values. Let's say minus 1. And it will be 1 minus 2. It will be minus 1. 1 minus 1. Okay, minus 1 is here. And then you can pick 2 here or minus 2. You will get here 2 minus 2 again 0. So you have 2 zeros here. Minus 2 0. Now you can also pick some points and you can see, so it verifies our graph is okay. Yeah, to make a precise graph, you can pick the points and place them on the graph. And for this one here, we have this basic function x cubed, and do we know its graph? Yes. Its graph looks like this. Its graph looks like this. We have at 1, we have 1 cubed. So I'm talking about y equal to x cubed. And if it is minus 1, then there's minus 1 and 0, 0. So it passes through these points. And now we have 5 plus 5. It means we will shift it 5 units up. So I will try to make it like this. So it will go up 5 units up vertically. So this 0 will go up. And then it will come to 5 here. So we'll have this one. Now it will be y equal to x cubed plus 5. Now you can also verify some points, like if you want to make a precise graph, you just pick some points and look at them 0. When x is 0, y should be 5 for sure. It's here, okay. And what about putting minus 1 here? So minus 1 cubed is minus 1. It will be 4 now. So if it is minus 1, it becomes 4. Okay, it has to be somewhere here. And then put minus 2, and you will see minus 2 is minus 3. So it means at minus 2, we have a sharp fall here. So it's better we can do, okay. So the real graph should behave like this. But since we are not using precise, measures here, so it's okay to have such thing. But roughly, our graph is something like this, It's just we will shift the y equal to x cubed graph 5 units up. So roughly, this is the graph. As I said, if you have a nice, grid here, like if you make the good squares and good measures, if you have a good sketching pad, you can also take the points and verify the graph. Now we will see horizontal shifts. So let's see. We will take it as a positive real number. So the graph of f of x plus c is same as the graph y is equal to f of x shifted 2 units to the left. So okay, now I will show you this. I mean, assume that you have f of x function, and its graph is okay. Let's say okay. I will use the x squared. Y is equal to x squared. Okay, let's say this is our f of x. Now, the graph of f of x plus c is same as the graph of this. This function is shifted c units to the left. So when you shift it C units to the left. So your graph will come to here, C units. To the left, it means it will come to negative C. So this is the graph of y is equal to f of x plus c. So as you see here, the x plus c, c is added to x, not y. So it's not added to f. It's inside here. It's inside. This is important. Now, if we subtract c, what happens? The graph of this new function is the same graph but shifted c units to the right. So it has to be this one here will be c units to the right. So in this case, we'll pass through c, and this will be y equal to f of x minus c. But be careful here. Since it's plus, the students tend to make it this way. No, if it is plus, it will go to the left, and if it is minus here, so it will go to the right. Okay, so be careful about this. This is the most common mistake here, because the students see it's plus here, it's plus, it has to go this way. They think no, it's plus here, it will go to the left. And if it is negative, it's minus c here, it will go to the right. Okay, let's see an example of this. Look at this function here. Look at this example. In this example, it says sketch the graph of f of x equal to x squared, then do this one, x plus 2 squared and x minus 2 squared. Now think of this as f of x. So this is equal to f of x plus 2 squared, right? And this is like gx f of x minus 2 squared. So then you can use the graph of this function here, the real function, the basic function. The base function is x squared. So we are shifting it 2 units, and 2 units to the left, 2 units to the right. Now if you make the graph of these functions, so you will start with x squared, so it will be x squared, then 2 units to the right, it's minus, so right, 2 units, and plus to the left. So this will be x plus 2 squared, and this is y is equal to x minus 2 squared, and this is y is equal to x squared. Okay, we'll see this in in the slide. It's already given here. So we will shift it to the left and right. You see this is the main function, y is equal to x squared. It's x squared. And now this is y is equal to x minus 2 squared. X minus, so minus will shift it to the right, and plus will shift it to the right. I mean left, sorry, 2 units to the left, so you will get this one. So this is the graph of G, and this is the graph of H. Now let's do the try and check exercise. It says sketch the graph of f of x equal to absolute value of x minus 3, and sketch the f of x equal to x plus 5 cubed. Now first, of course, here you can, as I said earlier, and I repeat all the time, you can make this x y table and find the ordered pairs, and you can do this. But we are not interested in this. There's an easy way of doing this if you know some basic functions, like for example absolute value of x, and we have this x minus 3 here. So as you see, x is replaced here inside the function. X is replaced by x minus 3. So if this is a function of g of x, let's say this is g of x minus 3. So for this reason, we see a horizontal shift here. So now, do we know the graph of y is equal to absolute value of x? Yes, it's a V shape. We already know that. So now we have, instead of x, x is replaced by x minus 3. In this case, the function should be, since this is minus, it has to go to the right. So it means this one will go 3 units to the right. So then we will get the graph of y is equal to the absolute value of x minus 3. Now, in the same way, we can look at this function here, x cubed plus 5, x plus 5 cubed. Now, first, is there a basic function we can use here? So this is cube, and there's plus 5 here, so it seems we can use x cubed function, and now x is replaced by x plus 5. So then we have x plus 5 cubed. So you can take it like if this is the function gx, so this is now the Young function gx plus 5. So as you see now, the function changed and x is replaced by x plus 5. So it gives us a horizontal shift. Now, do we know the graph of y equal to x cubed? Yes, we know it's like something like this. And think of the graph of this. So x is replaced by x plus 5. It means it's a horizontal shift, so it's a plus 5 here. So plus 5 means this side, how many units? 5 units. So from 0 to 5, it will go minus 5 up to minus 5. And we will have this graph here. Okay, so this will be, okay, roughly it will be this graph here. So the same graph, but 5 units shifted left. So this is the graph of x plus 5 cubed. But if you have a precise paper and with the squares, you can take the points, you know, and check the points here, and you can make a precise graph. But here in our section here, we want to get an idea of the graph by using the previous knowledge. So it's y if x cubed, so it has to be x cubed shifted 3 units left. Anyway. Now, graphing functions using reflections. Now, the graphs of some functions are reflections of the graphs of other functions with respect to x and y, x or y, or the origin sometimes. Okay, now we will see reflection across the x-axis. For example, this is the main information here. The graph of minus f of x, y equal to minus f of x, is the reflection of the graph of y equal to f of x across the x-axis. Now, what does this mean? It means if this is the graph of y equal to f of x, then what is the graph of y equal to negative f of x? So the graph of negative f of x is this one here. So you take the reflection of f of x with respect to x, then you will get the graph of y is equal to negative f of x, as you see here. So if your graph is something like this, for example, this is y is equal to f of x, then what is minus f of x? So what is it? Then you will take the reflection through the x-axis, so you will end up with this, for example. So this will be y equal to negative f of x. So negative f of x is the reflection of f of x across the x-axis. Okay, this is the main information you have to know. So this will allow us to do to make the graphs by using the reflection across the x-axis. For example, you have negative x squared. Of course, you can do usual graph plotting, sketching procedure, but no need for this because we already know the absolute value graph. So, sorry, the x squared graph, it's this. But our information says negative x squared. If you have negative of this, so you have to take the reflection of this graph with respect to x-axis. So its graph should be So minus the graph of minus x squared is just a reflection of y is equal to x squared graph according to or with respect to x-axis here. So this will be our graph. Now you'll see it here. Now let's look at this try and check example. And here, the first thing you have to see is the graph of this function. Remember that this was the graph. The graph of this function was something like this. No inputs on the negative side, and the graph only works for the positives. This is y equal to absolute value of x, no, square root of x. Now, since we have minus here, so the graph of y is equal to negative square root of x will be its reflection across the x-axis, so it has to be like this. So you see the difference here. It's I'm taking the reflection of this, and I get the graph of y equal to negative square root of x. And of course, if you want to take the some points and make the table and put points here, yes, you will get the same graph. Reflection across the y-axis. Here is the important thing to know. If the graph of y equal to f of minus x, this time x is replaced by minus x, is a reflection of the graph across of the graph of y equal to f of x across the y-axis. Now, here, when you have f of x, then it's changed to f of minus x. So, if, for example, sometimes it doesn't change the things. For example, like if your function is just x, so it becomes minus x. Okay, there's a change. But if this is x squared, what do you get? It's the same thing. So the graph will not change. But here the graph changes, as you see, because the graph will change because we have different formulas. Now, you will see them on the graph. Now, look at the example here. So, in this case, if this is the function f of x, then the graph of f of minus x is the reflection of f of x across the y-axis. So it means across the y-axis means this. You're taking a point and you're taking its reflection with respect to y point. Take this one here. Take this one, it's here. Take this one, it's here. So take this one with respect to y, it's here. And take this one, it's here. And do the same things here. With respect to y, it will be this. With respect to y, it will be this. So you will have the reflection of f of x with respect to y-axis. So remember this. It's when we do it if x is replaced by minus x. So x is replaced by minus x. Now let's look at this example here. Now, sketch the graph of f of x equal to square root of negative x. Well, we know this graph, this function indeed. This is it has this type of graph, and it doesn't have any values for the negative side. So the inputs or the x values are not here. Now x is changed to negative x, so it's y is equal to square root of negative x. So according to our rule, the graph of this one, will be the reflection of graph of y is equal to square root of x. So we have to get something like that. So its reflection will be here, the y-axis here. So you're taking the reflection of this graph. So you take it to this side. And now, this is the graph of y equal to square root of negative x. And now you can ask this question, how does it become the the graph on the negative side because the square root does not take the negative values inside, so this doesn't make sense. Is it so? Okay, let's check. We all can pick some numbers here. Look, let's take 0. Okay, 0, 0 is okay. Now take a point here, -1 becomes -1. So look, this was the rule here. This was the function rule is square root of negative x. So it will have square root 1, which is 1, right? So here -2. So -2 makes square root 2, which is about 1.4. So as you see, there is no problem with this. And if you take a point from here, for example, take 2, let's see what happens. X, y, put 2, and then you have square root -2, and this is not a real number. So not real. So for these points, the function doesn't work. So this graph makes perfect sense. So there is no problem with this function, with this graph. So then you can say the graph of the function is this one now. Okay, let's see the solution here. It tells exactly what we did, like the square root of x and the square root of negative x, and x is replaced by negative x. So then you take the reflection through the y-axis. Now, now let's look at this try and check example. Now let's look at here. Sketch the graph of negative x plus 1 by reflecting the graph of x plus 1. Now, what is the graph of x plus 1? This is a line, so you can pick 2 points, 2 ordered pairs. I will say 0, it becomes 1, and 1, it becomes 2. So 0, 1 is a point, and 1, 2 is another point. So then this is y is equal to x plus 1. Now, here in this graph, in this function, x is replaced by negative x. So now in the new one, you got y is equal to minus x plus 1. X is replaced by negative x. So it means you will reflect the graph of this graph with respect to y-axis. So you have to make the reflection this way. And on this part, it will go this way. On this part, it will go this way. So you will have something like this then. At 1, we have the same issue here at 1. And then this become 1, 2, goes to -1, 2. And then this part will go to this part. So you will have this. Like this is how to reflect it with respect to y-axis. And if you want to make sure about the points, you can pick some points, put 0, you got 1, and put like, let's say 1 here, you got what, 1, so it will be 0, as you see it's here, 1, 0 is here. And then you can put some more points here, 2, -1, that will be 2, -1 will be somewhere here. As you see, it's compatible with the ordered pair, so this makes the graph. Now vertical stretching and shrinking. Stretch means here you pull, okay, you take one thing and you take it with your hand, and then you pull this here. Okay, my drawing is not good, so take this one and then you pull. So then it becomes like this. Okay, so this is stretching. Okay, stretching. So it's short. Now it became long. Okay, so this is called stretching. So you pull it apart. So it's stretching. And shrinking means the reverse. Okay, the stretching is this, and the shrinking is this here. So the reverse of the or opposite of stretching. So opposite of stretching. Stretching. Okay. Now, so we will think of vertical stretching. Vertical stretching means this, it was something like this, so you stretch it, so you make it bigger. And then shrinking, it was like this, so you shrink it, so it became like smaller. Okay, this is called shrinking, and this is called stretching. So you make it bigger, and this is stretching. I mean, you make it longer, so it's called stretching. You make it shorter, it makes shrinking. So now what we'll see in the functions graph, we do it sometimes. Now here is the idea: if f of x y is on the graph of y equal to f of x, then x cy is on the graph of y is equal to c f of x. So what does it imply? It says, it implies this: if c is between 0 and 1, then the graph of y equal to c f of x is the vertical shrinking of the graph of the function f of x by a factor of c. C here is less than 1, as you see. So it's like you have f of x. So now you have f of like 1 over 2 f of x. So now here, as you see, the value of f of x doesn't change for any x, but the y values, as you see, are changing. It's like y value is now halved. So it became half of f of x. So y values are becoming shorter. So it gives you a vertical shift. Now it's like if xy is here, and then the new xy should be somewhere here. So if it was like f of x here, f of x, and now f of x plus x f of x over 2 is here. So it becomes shorter. So it's a vertical shrinking. Y values are shrunk. So here, Y values get shrunk. Now, the other, okay, here is the thing, like on the graph, you see it this way, like the x's corresponding to f of x, now it becomes half. So it goes down, the y values are changing, and it becomes, this heights are becoming shorter, you see. So this is, we call it shrinking, vertical shrinking. It's like we are pressing the graph from, vertically on both sides, then you got a skinny graph. Now, if c is bigger than 1, in this case, you have the vertical stretching. So it means like you have f of x. Now, assume I made it y is equal to 2f of x. What happens? Now, y value is doubled. So it means if you have a point here this on the graph x, y point, f of x, so now f of x becomes 2f of x. So it will go, this point on the graph will go here. So it will make a stretch. Now, as you see here, so this is x, f of x, but in the new graph, so x will correspond to c times f of x. So let's say c is 2 2 times f of x. As you see, the arch function changed. Now y becomes c times f of x. So this time we stretch it. So we pull it this way, we pull it this way, it becomes stretched. It's called vertical stretching. Now sketch the graph of y is equal to 2x squared and y equal to 1 over 2x squared roughly. Here it uses the word roughly. It means like compare them with the x squared. So x squared is this. You know, we don't we are not precise here. We don't put the points here. We don't make a precise graph. So it's asking it to do it roughly. So it becomes 2. What does this mean? It's like doubled. You know, the y values are doubled, so x values are same. So y values are doubled means it will go double here. So it will go double. So x values are here, but the y value will go double. So then we'll have this 0. It's when it's double, it's the same. So here, look at the y values that they will be, if it's here, so it will be doubled. It will go here, and y is equal to 2x squared. So in this case, y equal to 2x squared, it will be doubled. Y's will be doubled. So here, if it is here, any one will be doubled. You see the difference here? It's doubled. So these points will have this one. It's doubled, you see, this one. This distance is doubled. So this will be our new function. And in the same way, it's 1 over 2. It's 1 over 2 means like it will go down to half. So you will get a graph something like this now. Now, okay, you can see them here. So y is equal to 2x squared. As you see, it's doubled here, 2. Y is doubled here. X same, but 2 makes the y doubled. So x, for the same x value, this is what we get, x squared, and now this makes the half of it. Like you get this half, and here it makes it doubled. Okay, so this distance and this distance are same here. So it's doubled. And this is halved. You see here. So y values doubled, y values halved. So this is the y value. Y value means the height, okay? So y values are corresponding to the heights of the points. Y values, heights of the points on the graph. And if you want to do a precise graph, I mean, it's better you take the points here and you plot the points, like the order pairs, and make nice graphs. But we did it, you know, roughly to see the vertical stretching, like using this property here. Now we will see horizontal stretching and shrinking. Now this time everything happens in horizontal axis. So it's horizontal stretching is this, and shrinking is this, let's say. So you go from both sides and you shrink it. Okay, shrink, and this is stretch. Okay. Now, the key idea is this: if xy is on the graph of y equal to f of x, it means y is equal to f of x. And then 1 over cx, comma y is on the graph of y equal to f of cx. Okay, let's see how it's true. Like put x for 1 over xc, so you will get 1 over x, 1 over cx. So then you write c here. So we are putting this in here. So it will be f of cx 1 over cx, so it will be x here. So we'll end up with, again, for the same y value, y is equal to f of x. So this is the mathematical fact behind it. Now, what does it imply? It implies this: if c is bigger between 1 and 0, the graph of f of x, f of cx is horizontal stretching of the graph of y equal to f of x by a factor of c. Now, the key thing here you have to see is this one here. X is replaced by cx. So now, if you see this one, x is replaced by cx, then it will be a horizontal stretch or shrinking. Now, c here can be less than or less than 1 or bigger than 1. Now, as you we will see that the bigger than 1, less than 1 case, it's this. So c is f of x, is this one here. C is f of x, and now cx is this one. Now assume we have this 2, 5. Okay, assume f of 2 is 5. Now, if c is 1 over 2, let's take the 1 over 2 here. C is 1 over 2. So how do you get? So if you put 4 times, okay, 1 over 2 times 4, it will be again 5, right? Because it will be 4. So f of 2 is 5, so that you get f of 2 equal to 5. So here you got 4, but in the new function, what will give you the new 5? It will give you 4. You see? Now, it means this. If this is x, y, to get the y level, the same y level, you will end up with x over c. So if c is 1 over 2, that x becomes, this one becomes x over 1 over 2, so it becomes 2x. Your x goes double here. So then you see the stretching here. But you can also see the same thing on the graphs. I mean, on the by plotting the points, you can see it. It requires a little bit thinking. It's not easy to see when it is done with C and theoretical stuff. But anyway, we will see them in the examples. Now, in the same way, if C is, we will call this one stretching, horizontal stretching. So you take the legs of this parabola and you stretch them toward the sides, to left and right. And if c is bigger than 1, then the graph of y equal to cx is horizontal shrinking. It's the graph of y equal to f of x shrinking of the graph by a factor of c. And c is bigger than 1. Now here, again, let's use this idea here. If this is x here, now your x again will be x over c, but if c is 2 here, if it is bigger than 1, so instead of x, you will see x over 2 here. So your graph for the same y value, your graph will come to x over 2. So this is the idea. For this reason, it's shrinking. Anyway, now we will see it more on the exercises. Example, sketch the graph of y equal to 2x plus 1 and y equal to 1 over 2x plus 1 using the graph of y equal to x plus 1. Like, indeed, these are all line equations. You can, make the graphs of them by just plotting points to points. And now I want to, we can do that by, making the table here, by picking 2 points here, and then we can make the graph. But we are not interested in this. We want to see how the stretching work here. Now, the first thing you have to, okay, we will take this one as our base function. So as you see, y is equal to x plus 1. Here, when you change it to this one, becomes 2x plus 1. So as you see, x changes to 2x. So you can say this x changes to 2x, it means like a horizontal stretching, or okay, 2 is bigger than 1, so it's a horizontal what? It's horizontal shrinking. Now, when x is changed to 1 over 2x in here, we will get the graph of 1 over 2x plus 1. This c here is less than 1 and bigger than 0, so it will make a horizontal stretching. So now, horizontal shrinking and horizontal stretching, let's see them on the graph. Now this is y is equal to x plus 1. This is the original graph, y equal to x plus 1. Now we do this horizontal shrinking for this one. Horizontal shrinking. Shrinking means like push to the inside. I push from left and right. So we push it this way. We got, and push it this way, like you're pushing it toward the middle. So you will get this one now from the outside. So from the left and right, you push it, so it becomes this line here. And now you push this one here. So we will use the horizontal stretch. And if you stretch this one, it will go this way. If you stretch this one here, it will go. If you stretch it, it will go this way. So you will get this type of graph, this type of line. So in stretching, it's a horizontal stretch or shrinking, sometimes it's hard to see the things. It's better if you want to be precise, you can make the table and see them here. But theoretically, what we expect from you is like not to draw it indeed, but to ask you, okay, if you see this too, what does it mean? Like how the graph changes to this one. So you say it's a vertical shrinking, or horizontal shrinking, or vertical stretching. Like we expect it from you, because this, since the graphing only by using stretching or shrinking, it might be precise. So we want you to tell us when you see this and this. So what's going on here? It's a vertical stretching or horizontal stretching or shrinking. We want you to tell this to us. So this is wanted from you. Graphing functions using multiple transformations. Now sometimes you don't see just one transformation, but you have more than one. So for example, you have a basic function x cubed. You might have x minus 1 cubed. So what does this mean? Okay, we will discuss it. If you remember it, this x is replaced by x minus 1. Okay, this has a meaning in graphs. And then after this, we add some number here, so it has another meaning on the graphs. One of this horizontal shift, and the other is vertical shift. Now, with this means shifting it 1 unit. You remember it, like x is replaced by x minus 1. So shifting it with 1 unit, right? And then adding adding the function an extra number here, it will make it shift 7 units up. So then these transformations, shiftings, can be, back to back. And here, square root of x, for example, what can you do? Like, for example, this x minus 1, x is replaced by x minus 1. What does it mean? It means like shifting it 1 unit to the right. And now you change x with minus x, you change x with minus x. This has a reflection thing, remember this reflection. So reflection with respect to y-axis. And then again, if you subtract from the function -2, it means 2 units down. So as you see, we shifted 1 unit to the right by doing this transformation, and then reflected through the y-axis, and then shifted 2 units downward. So as you see, we can, to graph this one, we can use the basic function. So if you know what to do, what types of shifts and reflections you do, you can get to here, or you can get from here to here by using appropriate shiftings and reflections and maybe stretchings. This is the lesson we have to learn here. By using different shiftings and reflections, we should be able to graph them by using the help of the basic functions. Of course, we don't always close the door to the XY, using the plotting. Yes, you can do the plotting and make the graph like that, it's okay. But what we want from you is to tell how to get the graph of this function from the basic function. Now let's look at this example here. Just to sketch the graph of the following functions by using x squared. Now look at here. I mean, you can see it. There's a 2 here, 2 going on, and then there's this +4. It's better you start from x squared and you list what happened, like x squared, so it becomes 2x squared. What happens? You got f of x, then you have 2 times f of x, and then you have +4 is coming here. So then you have to tell what type of shifts and what types of transformations are done. Okay, let's see. This is here. X squared becomes 2x squared. 2x squared, so it makes a vertical stretching. And now we have a +4, so this has to be shifted up. So look at the other question here. Now let's look at part B. And the idea here is, to approach this problem is this. Let's start with the basic function x squared and try to get, by using the steps, try to get this one. There are several ways you can do it. One way is going to x squared, then making it x minus 3 squared, and then multiplying with a minus sign here. So here, if you have a function here, as you see, this will be x minus 3, and then you can, if you don't want to do it by using the function, you can say your x is replaced by x minus 3 for sure. So this becomes what? A horizontal shift to the right. Okay, we have minus, it becomes to the right. And now here, the function itself is multiplied and becomes minus f of x. So what you have is x remains same, but y changes to negative f of x. So you make a reflection through y-axis. So if you don't remember these, please stop the video and go back and see this sections, like how to do the horizontal shift in the reflection through the y-axis or the x-axis. Go back to these, go back like 10 slides back, you will see this. We already covered this one, but maybe in one lesson it's not easy to see, and you cannot memorize all of it in one lesson, so you have to go back and check to remember them. Okay, this is one way to do it, or you can do it in different ways. Another way is, this is another way, another path to go. You can do it with this, like x squared becomes minus x squared, so it becomes a reflection through the y-axis, no, through the x-axis, and then after this you change x with minus x squared, minus x minus 3. So here there's x squared becomes minus x squared. You multiplied with minus. The function itself is multiplied with negative. And this x here is replaced by x minus 3. This becomes a shift to the right. And this becomes a reflection through the x-axis. You can do them in these two ways. So now you can do step by step. First, you can go from x squared to x minus 1. This in the first step it says x squared goes to x minus 3 squared. So you can shift the graph by 3 units. Then you get this one. And then the second step is now we are here x minus 3 squared. So how to make this one to minus x minus 3 squared. So that there's a function and we have this negative of this function. How do you get that? You get that by flipping it through the x-axis or reflect it through the x-axis. So you say okay, the second part, I got this x minus 3 squared becomes minus x minus 3 squared. So you see x, it's minus, okay? So it means the reflection, there's a reflection across the x-axis. So you reflect this function across the x-axis and you end up here. So this will be the graph of this function. Now, if you want to also, you can also see it by doing the plotting the points. You can verify this. Oh, this is not true. Yeah, this is true. For example, you can put 3 here. So what happens? You get 3, you got 0. And assume we got x equal to 0. What happens when you get x equal to 0? You got here minus 3 squared, which is 9. Then with this minus, it will be minus 9. Is it so? 3, 0 here. And then we have 0 minus 9. Yes, at least two points are compatible. And let's take, for example, 4. What happens if we get 4? So this becomes 4 minus 3 squared. It's 1. Minus 1, so it will be minus 1. So 4 makes minus 1. Is it true? It has to be minus 1 here. So this here, don't pay attention to this graphs that much. They're not precise, but when you do a good scaling, then you can see that the points will fit in here. Let's do this try and check. Again, we will check these graphs by using the appropriate transformations to a basic function. Now you can start by x cubed here. The x cubed is the basic function. From x cubed you can go to x cubed plus 2. This is the first step. And then x cubed to minus x cubed plus 2. This is the second step. Now this is making a vertical shift. Okay, if you don't remember this, please go back to the slides and see, because this is a function here. This is the function plus 2. So it means if you have this graph, then we have plus 2 here. We will make it 2 units up. So it will be 2 units up. This graph will be 2 units up. And then we have this function, but this is multiplied. The function is multiplied with minus. So this becomes, the second part becomes the reflection through the x-axis. So the f of x becomes minus f of x, right? So this corresponds to the reflection through the x-axis. Now we reflect the second graph. So we reflect it through the x-axis. When you reflect it through the x-axis, it has to be this, and then this will be here up to here. It will go up to, okay, something like this. So this part will be like that, and this part will be like that. So the graph will look like this. Now, if you want to verify the graph looks okay, so you can pick some points and see if it looks okay. Not precisely, but at least are the points are in the same, I mean, are on this are on the appropriate quadrants. You can check them. Put 0, you got -2. Is it so? Yes, it's -0, 2. It's okay. And what about 1? If you put 1 here, it will get -3. If it is 1, then you get a lower value. It's okay. It looks good. And how about making -1? Let's see. When you put -1 here, you get +1, but with this minus, it will be -1. So -1, it has to be somewhere here. So it looks kind of okay. And you can put some more values like here -5. And when you put here -5, you will end up with -123. And with this minus, it will be plus. So you got -5 is corresponding to +103. So it's somewhere here. But the graph looks fine. So this is the graph of y is equal to -x cubed plus 2. Now, let's do the other question here. There is this square here. We see the square. So square will tell us what to do. You can take the basic function as the x squared. So you can start from the x squared. And x squared becomes x plus 3 squared. And then we multiply this with 2. And then we add this function 1. So we have lots of transformations here. So look at here. This transformation is a horizontal transformation. This is a horizontal shift. So x is replaced by x plus 3. Horizontal shift to left. And then we multiply this function is multiplied with 2f of x. So it means the y values are doubled. So it means a vertical stretch by 2. And here there's this +1. This is a function here, and this function is added to a number. So like c. So this is a vertical shift upward. Okay. Vertical shift by, okay, upward by 1. So let's do it. This is x squared. Okay, we are doing everything roughly. Okay, so no need to be precise. I mean, you can check with the numbers at the end. You can check with the points like x plus 3 squared. So this will come to here, the left. So we have this one. Now the stretching issue will stretch it. So when stretching it, this becomes the same. Just because this y is equal to 0, when you multiply with 2, it doesn't make anything. I mean, it doesn't go up. So, but the others will go here. It will make this y values will jump. So it was y value here for the x, so it will go double. So then you will have a narrow picture here, narrow parabola, thinner. And now this one is vertical, so we will shift it 1 unit up. So this one will go up 1 unit. And we'll have this narrow parabola here. Roughly, all graphs are here roughly. I mean, if you want to make sure everything looks fine, you can take points and put the points here. Like when you put 0, it will go up to 3 squared, 18 times 2, 30, 37. So then it's for 0, it will go something like 37. So it has to, I think yeah, it looks fine. Like this, right leg is, going up and up. I'm sure somewhere here at 37, it has to touch the y-axis. And also you can check the other points, like put -3, you will see it's 1. For example, put -3. When you put -3, it makes 0. It makes 0 here, 0. It's +1. Is it true? Yes. You can put also some value -4, and you will see -4. If you put -4, what happens? -4, it becomes 1. 1 times 2, 2 plus 1, 3. So it has to go like 3 here. Yeah, everything looks fine. So roughly, we got the graph. So this is our graph. As I said, in the shifts, like stretching, it's a little hard thing, but the other shifts, you should be able to do them on the graph. And also we'll ask, when we give them to you, then we will ask you which transformations are done to get this. I mean, I don't think it will be hard to graph them, to ask the students to graph them, but we can ask, like, what are the appropriate transformations to get this function from the basic function. Okay, I think that's the end of it. Thanks for watching. Please review the slides again, because this is a hard topic.